getting them out is definitely a challenge.
I like looked it up, but
Yeah, I know. I took me a couple hours, and I think I just figured it out the other day. So back to the graphs of logs. So the big thing, what's all the chitter chatter over there? Is that Chris Brooks all of a sudden coming out of his shell? Oh, okay. All right. If you think about your features of exponential graphs, where the x-axis is an asymptote, and it kind of, we'll just do growth for the moment, that's your exponential. So if we were changing this to exponential form, it would be the base of 3 to the y power equals x, correct? We learned that translation yesterday. This and this are the same thing. So when we want to invert it, it's going to be 3 to the x equals y. So let's pretend that this is y equals 3 to the x. We have an asymptote of the x-axis in the exponential graph, which means in the log graph, the y-axis becomes our asymptote. That switches. We had a y-intercept of 1. That means in the log graph, our x-intercept becomes 1. So 0, 1 becomes 1, 0. That's a y-intercept becoming an x-intercept. Good? And if this is a vertical asymptote, then as we get closer to it, we're going to kind of almost look as though we're parallel to it. So, a couple things. If I were to plug in a 0, and maybe now is the time where I show you on your calculator. And whose is not in decimal? Alpha y equals. Yours is infinitesimal. Oh my word. Is there anyone who's not?
If you don't say decimal, then maybe at the top.
Yeah. We gotta be here. Depends on who clears your calculators last year. Yeah, we were supposed to do it a certain way. Why is here? You don't have alpha y equals. That doesn't work. Okay. Oh wow, you're calculating a lot. Who is it not? Yes. Okay. So there's two ways you can get to it. Even if you're in Tesco, you can at least see where it is. If you hit alpha y equals, and then select the function one, which would require hitting the window button. So alpha y equals brings up this, but we want function. So we want to hit the window button, and that will select that menu. And then option 5 on Lucas's computer. Wow, this is really freaking out. Log base. So if you scroll down and hit that, now if yours is blocked out, we have to fix that. But log base, here's what I'm going to tell you now. This is actually great. I'm actually maybe glad that a lot of yours is log base 3 of 0, and you can just plug it. So you can't on yours because a lot of yours are in test mode, but this gives you an error because at the end of the day, you're being asked 3 to what power gives you an x of 0, and that doesn't happen, right? There's no way you can get 0. Agreed? 3 to the first doesn't work. 3 to the 0 power doesn't work. Sorry. That doesn't work, so that does not exist. Nor should it. Because at an x coordinate of 0, that's your asymptote. So it shouldn't hit it. And the graph won't. If we do 1, 3 to what power gives us 1? Right? 0. 2 is not going to be a nice one to check because log base 3 of 2 means 3 to what power gives us 2. And that's not going to be a nice number, so let's just skip it. What's the next nice number that we can do? 3. So we'll do an x coordinate of 3. Log base 3 of 3. 3 to what power gives you 3? The first. What's the next nice one going to be? Yeah, you're right. So let me just rephrase how this is working. This is the same thing as 3 to the y power equals x. So it actually makes more sense on your table of values, and this is the first time this has ever happened, to choose your y values. 0, 1, 2, because 3 squared will give you an x coordinate of 9. 3 to the third will give you an x coordinate of 27. So it actually makes, because that's the same thing as this, it actually makes more sense to choose your y's. And then when you plot those points, you have 1, 0, 3, 1, 9, 2, and we're not going to get to the other one. But we're not going to reach a y coordinate of 3 until we get to 27. Good? So let me teach you something right now that all of you can get around your test mode right now. If you're asked for log base 3, oh, I would have needed that. Thank you. If I do log base 3 of 9, let's pretend we couldn't do that one in our head or something. Here's what you all can do to get around it. This is called the change of base formula. So like Jason, your calculator doesn't even have that log base functionality. You're going to have to do this. Okay? If you type in the log of 9 divided by the log of 3, and you all can do that whether you're in test mode or not, you'll get your answer. What does it give you? Everyone can do this, test mode or not. Just use your regular log button. Type in log 9, close your parentheses, divided by log 3. 2. Did everybody get that? Does that make sense? So we're actually now, this is the change of base formula. If you have the log with a base b of x, the change of base formula is what your calculators, like an older calculator that doesn't even have that log base option, uses. You do log of x divided by log of b, and it's the same thing. And all of your calculators will do that. Okay? So if we want to graph this, go to your y equals, and Faye, what would you have to type in? The change of base formula. How would you type in log base 3 of x? Like, I want you to translate this to an equivalent expression. Look at your formula. Which of these two is on the numerator? The x. So which of these two will be on your numerator? The x. The b is what's on your denominator. So what will be on your denominator here? The 3. So we'll type in the log of x divided by the log of 3 and graph that. What do you have a drinking fountain in the background for? Oh, can you? Yeah. Well, it makes it very difficult to see, but it's this blue line here that comes down and never, pass that back to him, because if we're going to do the change of base, So now that we've given you the change of base, there's 2 ways you can rewrite a log function. One is to rewrite it exponentially, to translate it. The other one is rewriting it via the change of base formula, log of x divided by log of 3, which we just did. If you're going to use one of those to graph this on your calculator, you can't do that one. You can't do the exponential one because that says x equals, and we all know our calculator has y equals logged in there. People that are borrowing these up here, are there any of yours that say r equals? Because I have another class in a different mode completely, and so just if that does happen, just tell me. So log of x divided by log of 3, so I get a better look than what Lucas's gave me with the drinking fountain in the background. There it is. Okay? So it kind of looks like it stops It doesn't. It's going to go down forever. It's getting infinitely close to the y-axis. If I change my window a little bit, I'll see it a little bit more clearly. Even if I go between 0 and 1, I'll see it even more clearly. That it goes down forever and ever. Okie doke. All right. So that's that. The inverse of this equation is switch the x's and the y's. Done. And then let's just translate it. So 3 to the x equals y. That's kind of what we did to start. Just highlighting again that the exponential is the inverse of the log. The critical points for you guys on a log function are 1, 0. Because for exponential it used to be 0, 1. And for exponential it used to be 1 comma whatever your base is. So this one is base comma 1. Which in this case the base of our log was 3. Hence the reason 3, 1 is on our graph. Does that make sense? Asymptote is the y-axis. The equation of that is x equals 0. Okay? Domain and range of a log function, or should we go exponential? Of an exponential, your domain is all real numbers. Agreed? Negative infinity to positive infinity on your x-axis. Your range, however, on an exponential is from 0, not including 0 because that's an asymptote, up to infinity. So because they're inverses, those are just going to flip-flop for your log function. X can be any real number. X, that little c with an e in it is an element of. So you can say x is all real numbers, that'll work. But you should know what that is because they could put that in a multiple choice and you don't want to be, out in left field on it. That means that all of your x's are elements of the real number system. So x can be any real number is all that says. Okay? So when we go to do our log domain and range, those are going to flip. Our domain, look at your x coordinates, are now from 0 to infinity, not including 0. And our range is from negative infinity to positive infinity, which is all real numbers, but this time it's the y coordinate is any real numbers. This idea of the domain came up last night on your homework. The domain has to be between 0 and infinity, can't equal 0. In other words, if you go down here to this log function, x has to be anything greater than 0 to infinity. You're not allowed to take the log of a negative number, and you're not allowed to take the log of 0. You're only allowed to take the log of positives. So write that. Log of positive numbers only. So in that one, another way of writing the domain is just that x has to be greater than 0. The range can be anything, so y can be all real numbers. Okay, so now graphing logs with some transformations. The parent graph here is log base 4 of x, which means it contains, and I'll write parent next to this one. Our parent graph contains 1, 0, and b comma 1, which would be 4 comma 1. Those are the points on our parent graph. What transformations, there are 3 of them, does this one undergo? What comes first, do you think, Vince? Shift right 1, very good. So we're going to take these original points and we're going to go right 1, followed by, so he handled the -1 on the inside is right 1. Natalie, what do you think, what transformation would come next? Say it again. Well, the 4 is part of the parent graph. This is the parent graph, log base 4 of x. He just handled the log base 4 of x minus 1. So you got to decide, is it the 2 or the +1 that would come next? 2. And so is that vertical or horizontal? No. It's outside the parent graph, so it's a vertical. Is it a shift, a dilation, or a reflection? When you use a multiplier. Dilation, stretch or compression? Stretch by 2, good. And then the last one is, what does that do, Chris Brooks? Up 1, good. So not only that, but our asymptotes undergo that as well. The y-axis is the asymptote of the parent graph. So let's shift that first, or do, if we move a vertical asymptote right 1, does that do anything? Does it move? Yes, it moves over here. If you stretch a vertical asymptote vertically by 2, does that change it? No. If you shift it up 1, does that change it? No, it's still the same line, right? So your asymptote is right here at x equals 1. Now you used to have a point at 1, 0. That moves right 1. And then that stretches by 2, but since it's on the x-axis, we're not touching it. And then it shifts up 1, so that's there. That's now the point 2, 1. And the point 4, 1, 1, 2, 3, 4, 1, which originally would have been there, moves right 1. Now when that stretches by 2, it's currently 1 unit away, so we're going to double that. It's going to be 2 units away. And then it moves up 1 more. So think about that point from a numerical. If you move it right 1, it initially becomes 5, 1. Then when you vertically stretch it by 2, it becomes 5, 2. Then when you shift it up 1, it becomes 5, 3. So that's where that ends up. And your graph holds the same shape and just does that. Your domain has also changed. Our x-coordinate now needs to be greater than what number? Greater than 1. So you can either write x is greater than 1, or you can write 1 to infinity. Our range hasn't changed at all. That's still negative infinity to infinity. Okie doke. All right, so you really well picked up.